Section 7.4 is on graphing nonlinear inequalities in two variables. Wow, what a title. And just to remind you, we did exactly this last time, except we graphed linear inequalities in two variables. The only thing different is now we're doing nonlinear inequalities. So last time, remember, we graphed lines, decided whether to make them solid or dotted, and then shaded one side or the other. We're doing almost exactly the same thing this time, but now you're going to use nonlinear inequalities. In other words, they're not going to form lines, they're going to form parabolas. So the first thing you're going to do for a question like this, you can probably figure this out yourself, you don't need me, but what the heck, here I go, is you're not going to actually think of this less than sign, you're going to just think of it as equals. Y equals 1/2 x squared plus 2x minus 3. And we want to graph this, and it's a parabola. We know because it's a quadratic, right? It's a second degree polynomial. And it's not in standard form, so we could complete the square. But I'm feeling lazy, so I'm not going to complete the square. I'm going to use negative b over 2a. So that's negative 2, that's what b is, over 2 times a, and a is 1/2. So that's negative 2 over 2 times a half is 1, so it's just negative 2. So our vertex is at negative 2, comma, how do we figure out the y value? We stick that negative 2 into all these x's. So y equals 1/2 negative 2 squared plus 2 times negative 2, take away 3. So that equals, you got to do the negative 2 squared first. So that's 1/2 times positive 4 plus 2 times negative 2 is negative 4, take away 3. Half of 4 is 2, take away 4 I suppose, take away 3, so that's at negative 2, negative 5. Our vertex is at negative 2, negative 5. Sorry for squishing it in there a little bit. Negative 2, negative 5 is right there. And the a value is a half. So you could use a table of value, use some values close to negative 2, but I'll use a step pattern. And remember, it's half here. So instead of going over 1 up 1, I'll go over 1 up a half. And then instead of going over 1 and up 3, I'll go up 1.5, which will take me right here. Then instead of going up 5, I go up 2.5, right? I'm doing half as much every time. Instead of going up 7, I go 3.5. Instead of going up 9, I go 4.5. And that's all we're going to be able to fit. So then by symmetry, I can do all the points on the other side. It's nice to have this many points. We're going to get a very accurate parabola. The only problem is it's so hard for me to draw it on this board I use at home. Here we go. Oh wait, before we draw it, should I be making it solid or dotted? Well, if you take a look back at the original question, it's just y is less than, not equal to. So this should be a broken parabola. So I'll try to do that now. Okay, not bad. Now you're going to shade one side or the other. Parabolas is really easy. I mean, one way you can do it is you can certainly use a test point. So if we wanted to try the point 0, 0, the origin, you could plug it in here. You get 0 is less than, well, all of this, 0 squared times 1/2 is 0, plus 2 times 0 is 0, take away 3. Is it true that 0 is less than negative 3? No, it's not true. So in other words, this point 0, 0 doesn't work. All the points that work are on the other side of the parabola. But it's actually even easier than that when you have parabolas. You don't even need to use a test point. All you have to do is if it's less than, like this one is, it's below the parabola. If it's greater than, it would be on top of the parabola. Okay? It's that easy. Alright, you can also have systems of equations, or systems of inequalities, I guess. So here we go, we're going to graph this. We're going to have both of them, and then we're going to see where the shaded areas they have in common. So the first one we're going to graph is y equals x squared, and that's terribly exciting because it's the mother function. That is the mother function of parabolas. You should be able to graph this one very quickly. It has an origin at 0, 0, then a step pattern. It has an a value of 1, so over 1 up 1, over 1 up 3, over 1 up 5, same on the other side. So should we make it solid or dotted? Well, it's greater than or equal, so it should be a solid parabola this time. And you're left with something like that. And let's do the shading in a second. I mean, it's really easy. Again, it's y is greater than, so we know it's going to be up top here, but let's just wait until we do the second one. So the second one, obviously what we're going to be graphing is y equals negative x minus 1 squared plus 5. This is wonderful, it's in standard form, so we know the parabola right away is at positive 1, positive 5. positive 1, positive 5 is right here. It has an a value of negative 1, so that means it's facing downwards and it's congruent to the mother function. So again, it's going to be over 1 down 1, over 1 down 3, 1, 2, 3, over 1 down 5, 1, 2, 3, 4, 5, over 1 down 7 won't fit. So by symmetry, I can do this. And should I make this one solid or dotted? Well, it's only less than, not equal to, so this one should be a broken or dotted parabola. I'll try to do that now. Okay, I've got a couple problem areas there, but you get the idea. And so now we're ready to shade. So with the blue one, y was greater than x squared, so we said it was above the parabola. And for the red one, it's y is less than, so it's below the red parabola. Above the blue, below the red. Do you see the region that they which works here? This is the region that works right in there. So that is the solution to this system of inequalities. Every point in here works, as well as all the points on this solid line, or solid parabola, I suppose, not the points on this dotted parabola. Okay, now for something kind of different, but actually totally related. What we're going to do now is we're going to solve quadratic inequalities in one variable. So on the previous page, we were looking at graphing in two variables. Now we're going to solve in just one variable. What's different between these, x squared minus x minus 6 is greater than 0, and things like this? What's different is there's a y on this side, and there's not a y here. So what's kind of happened is we've replaced the y with a 0. So I want to use this previous question right here to help us understand what we're talking about here. Let's say that we had this question, but I'm going to do make it a question like on the other side of the page. I'm going to make it, I'll write it over here, 1/2 x squared plus 2x minus 3, and instead of saying that that amount is greater than y, because that's what this says here, greater than y, I'm going to say it's greater than 0. So really all I've done is switch that y to a 0. Now, even before I answer that greater than 0, let me ask you this. What if it said 1/2 x squared plus 2x minus 3 is equal to 0? Where's the point or points on this graph where 1/2 x squared plus 2x minus 3 is equal to 0? In other words, which x values, if you plug them into here and here, would you get a y value of 0? Well, a y value of 0 means it's right on the x-axis. So it would be right there and right there. The x-intercepts are where it's equal to 0. But this question doesn't say equal to 0. It says greater than 0. So where is it on this graph here, this parabola, where are all the points that are greater than 0? Well, all of these points are greater than 0. They all have y values greater than 0. And all of these points have y values greater than 0. And what we're interested in is which x values give you these points that are greater than 0. So if you looked at this left-hand side here with this yellow highlighted bit, all of the x values are less than, I don't know, it's about negative 5.1, I'm just guessing. But it's kind of like all the x is less than negative 5.1. All of those give you, make this amount greater than 0. Also, over here, if you look, all of the x values which are greater than 1.1 or 1.2 or something like that also give you points which are greater than 0. What about if this didn't say greater than? What if it said less than 0? Well, then you'd be interested in all the points down here. All these points are less than 0. They're below the x-axis. And so it would be all the points between negative 5.1 and 1.1. All those points are below the x-axis. They all have y values less than the x-axis. Less than 0, in other words. So we're going to solve quadratic inequalities in one variable, and I'm going to try to do an even better job of explaining this. So here we go. The first step is you're going to change the inequality to an equality and solve it. So why don't we do that? Before I show you the next step, let's do that. We're going to change this, x squared minus x minus 6, this inequality into an equality, and we're going to solve it. So how do we solve quadratics? We make them equal to 0, good, and then if we can, we factor. And we can factor this. This is a simple trinomial, so we have x and x, two numbers that multiply to 6 and subtract to 1. 3 and 2. 3 goes in the first one, 2 in this one, drag down the minus. A negative times a positive equals that negative, and it still equals 0. Now using the zero product property, either x minus 3 equals 0 or x plus 2 equals 0, and you can easily solve those. X equals positive 3 and x equals negative 2. Great, first step is done. Second step, use your solution, or solutions, in this case we got two solutions, as critical values to divide the number line into intervals. Whoa, that sounds confusing. It's actually not. You're going to make the world's easiest number line. Here's my number line. I'm only going to put these points on it. You can put more if you want, but I find it easier to put just these points on. Now don't do this. This is ridiculous, and people do this all the time. Why is this wrong? Because on a number line, the smaller numbers go to the left. So please make sure you put -2 down here because it's smaller, and 3 up here, it's bigger. Okay, you only have to put those numbers. If you want to put more, go for it, but I like saving time. So we've got intervals. We've divided it into intervals. We have one interval down here, below -2. We have one interval here between the two numbers, and we have one interval up here bigger than 3. Next step. Select a test value from each interval and substitute into the original inequality. Okay, here's why this will work. Because basically, these are the points, this x equals 3 and x equals -2, these are the x-intercepts. When you solve a quadratic equation like this, the points you get here, your solutions, those are the location of the x-intercepts. So we know there's an x-intercept here, and we know there's an x-intercept here. Now, there's only two possibilities. Don't write this down. I'm going to erase this in a second. There's only two possibilities. Either the parabola, because this is a quadratic, it's a parabola, either the parabola goes like this, and if we're interested in all the points that are greater than 0, we'd know where they are. They're between -2 and 3. That's one possibility. Or the other possibility is the parabola goes like this. And if we're interested in all the points that are greater than 0, it's all the points that are less than -2. Those are all greater than 0. And all the points that are greater than 3. Those are all greater than 0 as well. Now, you might say to yourself, well, how do we know? Maybe the graph comes back down like this again. How do we know that doesn't happen? Because if it did come back down there again, we'd have another solution down here. There'd be another x-intercept, and there isn't another x-intercept. When you get your solutions here, those are all the x-intercepts. So that's why we know the parabola is either like this or the other way around. And of course, you could just look at the a value, incidentally, and figure out which way it is. We know that it's like this. But what this method that we're working on here, what it kind of allows us to do is just focus in on this part of the parabola. We ignore the whole rest of the parabola and where the vertex is. That takes too long. All we're going to worry about is where the x-intercepts are, and then we're going to figure out for a certain point whether it lies above or below the x-intercept. Okay, so what this step asks us to do is to select a test value from each interval. So we're going to select a point from down here, below -2. Don't pick -2. -2, if you put that into the original inequality, you know you'd get 0 is greater than 0, right? -2 and 3 are the parts where it equals 0. So pick a point less than -2. How about -3? So I'll put here test. -3. If I put -3 in there, I get -3. I'm putting it in the original inequality. -3 squared minus -3 minus 6 is greater than 0. We're going to see if that's true. -3 squared is 9. Take away -3 is plus 3. Take away 6 is greater than 0. Is that true? I think so. 9 plus 3 is 12. Take away 6 is 6. 6 is greater than 0. Yes, this works. So these points down here, they all work. You don't have to try any more of them because we know the graph doesn't come back down again. We know that it stays either above or below. In this case, we now know it sits above because at the point -3, we get a value that's greater than 0. So we know that all these points down here work. And the way I like to draw it is to draw a line like that. Okay? Now we're going to try a point in between here. What would be the easiest point to try? How about 0? So if we put 0, we get 0 squared. Take away 0, take away 6 is greater than 0. So that's -6 is greater than 0. Did that work? No, it didn't work. So none of these points in here work. None of them. Now we try a point bigger than 3. Let's try 4. So we get 4 squared minus 4 take away 6 is greater than 0. True? 16, take away 4 is 12, take away 6 is 6, and 6 is greater than 0. Yeah, this worked. So all of these points worked up here as well. Okay, a little trick here to save you some time. When you're dealing with quadratics, like we are this year, you don't actually have to try all the intervals. Once you've tried one interval, then you know it's always going to alternate. If I tried this point and it didn't work, like in this case it didn't, then I know it went yes works, no doesn't work, yes works. If I tried 0 here and it did work, then I know it goes didn't work, yes works, didn't work. Okay, we'll alternate. The only time will be an exception to that is if you only get one solution. Like if you're on a number line you had 5, let's say. You'd need to try one point down here and you'd need to try another point up there. because they could both work, neither could work, one and not the other could work, so you got to be careful in that case. If you want to always be really safe about it, you could always try every single one of the intervals, but it's actually not necessary this year. Next year it will be necessary when we're dealing with cubics and quartics and stuff like that, but this year only quadratics. Okay, last thing, if it's less than or equal to or greater than or equal to, we have to include these points. If it's less than or greater than, we don't include those points, the critical points. So in this case, it's only greater than, so we don't include these endpoints, the critical points, so we leave them open like this. If it was greater than or equal to, we would fill them in. And that's it. Oh, one last thing. I need you to write this algebraically too. So I'm going to ask you to give me the answer graphically, and this is graphically right there. And I also need you to give it to me algebraically. So the way you do it algebraically, these points here, all those points to the left here, that's all the x's that are less than -2. And these ones up here, these are all the points that are greater than 3. Now we need a word here. What word should I put here? The answer, the x can be less than -2, or it can be greater than 3. You can't have and there. That wouldn't make sense. You can't have a number that's less than -2 and greater than 3. So you put or. In other words, any x that's less than -2 or that's bigger than 3 will work. And this is our algebraic answer. Okay, so this is graphical answer here. This is algebraic answer there. Okay, last one here. So the first thing we have to do is we have to make this equals, and we have to solve it. So in order to solve it, we're going to have to do mountains here. So we get 5x equals 2x squared minus 12. To solve a quadratic, you want to make it equal to 0 and keep the x squared positive. So let's move the 5x over. We get 0 equals 2x squared minus 5x when it comes over minus 12. Then we're going to try to factor. You can't take out a greatest common factor, so we're going to try to do Bobby Bridge. We're looking for two numbers that multiply to 24 and subtract to 5, and there are two numbers like that. The numbers that work are 8 and 3. So 2x squared minus 8x plus 3x, take away 12. Pair them up. So 0 equals, greatest common factor is 2x, and you have x minus 4 left over, plus greatest common factor is 3, and you have x minus 4 left over, so that worked. We have x minus 4 in both of them. You also have 2x plus 3. So 0 product property, either x minus 4 equals 0 or 2x plus 3 equals 0. If you solve this, it's obviously x equals 4. If you solve this, 2x would equal -3, and then x would equal -3 over 2. So there's your two solutions. You're going to put those on a number line. Make sure you put them in the right order. -3 over 2 goes here, 4 goes here. Now you're going to try test point. Let's just try one test point this time. What's the best test point to try? 0. What's the only time you can't try 0? You can't try 0 if 0 is one of the critical points. But it's not in this case. The critical points are -3 over 2 and 4. So I can try 0. So test, if I put 0 in the original, I get 5 times 0 is greater or equal to 2 times 0 squared minus 6. 5 times 0 is 0. 0 squared minus 6 is -6. And 2 times -6 is -12. Is 0 greater than or equal to -12? Absolutely it is. So this time, this worked in between here. So I draw it like that. That means that this one won't work and this one won't work because we said they're always going to alternate with quadratics. But next year you won't be able to do that. You'll have to test this one and you'll have to test this one. Last thing we have to do is we have to decide whether to make this solid or leave it circular. And since it's greater than or equal to, it should be solid. So it should be like this. Now we have to write it algebraic. This is the one that most of you don't like. The way you write this is you write the lower one, -3 over 2. Then you put less than or equal to x, and then you put less than or equal to 4. Incidentally, and you'll probably love this, remember you can also do it like this. -3 over 2, 4 with square brackets. And I suppose you could do that here too. The way you would do that here, the way you say x is less than -2 is you say -infinity to -2, or, and then the way you say bigger than 3 is 3 positive infinity, like that. So this is also okay if you want to give me that. And either one of these will work. Either this or this will work as well. Okay, there you go. A lot of information in today's class. I hope you understood.